Welcome to this video on number system conversions. We will explore how to convert numbers between binary, decimal, octal, and hexadecimal systems. Let's begin by understanding what these number systems are. The binary system, which has a base of 2, uses only 2 digits, 0 and 1. Next, we have the decimal system, the most familiar one, with a base of 10 employing digits from 0 to 9. The octal system has a base of 8, using digits from 0 to 7. Finally, we have the hexadecimal system with a base of 16, which uses digits from 0 to 9 in letters A, B, C, D, and F. Let's delve into the fundamentals of number systems, starting with the binary system. The binary system is a base 2 system, which means it only uses 2 digits, 0 and 1. This system is the backbone of digital computers, representing all data and instructions. On the other hand, we have the decimal system. This is the base 10 system that we use every day. It uses 10 digits from 0 through 9 to represent numbers. It is the most commonly used system in everyday calculations and human-readable formats. Now let's explore the octal and hexadecimal systems. The octal system is a base 8 system. It uses the digits 0 through 7. It is sometimes used in computing for representing binary numbers in a more human-readable form. The hexadecimal system is a base 16 system. It uses the digits 0 through 9, as well as the letters A, B, C, D, and F, to represent values from 10 to 15. The hexadecimal system is commonly used in computer programming and digital electronics because it provides a more concise way to represent binary data. Let's start with converting a decimal number to a binary number using the division method. Consider the decimal number 13. Divide 13 by 2, which gives you 6 with a remainder of 1. Next, divide 6 by 2, which gives you 3 with a remainder of 0. Then divide 3 by 2, which gives you 1 with a remainder of 1. Lastly, divide 1 by 2, which gives you 0 with a remainder of 1. Now read the remainders from bottom to top. The result is 1101, which is the binary equivalent of 13. Here's the Python code to achieve the conversion. The function takes a decimal number as input. If the number is 0, it returns 0. Otherwise, it repeatedly divides the number by 2, storing the remainders, and then concatenates these remainders in reverse order to get the binary representation. For example, when you input 13, the function returns 1101. Now, let's convert a binary number to a decimal number using the positional method. Consider the binary number 1101. Assign position weights, which are powers of 2 starting from the rightmost digit. The positions are 3, 2, 1, and 0. The digits are 1, 1, 0, and 1. The corresponding weights are 8, 4, 2, and 1. Calculate the sum by multiplying each digit by its weight and adding the results. This is 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1, which equals 8 plus 4 plus 0 plus 1, resulting in 13. Here's the Python code to achieve the conversion. The function takes a binary number as a string. It processes the binary string from right to left, and for each digit, if it's a 1, it adds 2 to the power of the digit's position to the decimal value. For example, when you input 1101, the function returns 13. Next, we will see how to convert from decimal to octal and hexadecimal. To convert a decimal number to an octal number, you can use the division method. Consider the decimal number 83. Divide 83 by 8, which gives you 10 with a remainder of 3. Next, divide 10 by 8, which gives you 1 with a remainder of 2. Then divide 1 by 8, which gives you 0 with a remainder of 1. Now read the remainders from bottom to top. The result is 123, which is the octal equivalent of 83. To convert a decimal number to a hexadecimal number, you can use the division method. Consider the decimal number 255. Divide 255 by 16, which gives you 15 with a remainder of 15, which is represented as F in hexadecimal. Next, divide 15 by 16, which gives you 0 with a remainder of 15, which is represented as f in hexadecimal. Now read the remainders from bottom to top. The result is FF, which is the hexadecimal equivalent of 255. Now let's see octal and hexadecimal to decimal conversions. To convert an octal number to a decimal number, consider the octal number 1, 2, 3 with base 8. Assign position weights which are powers of 8 starting from the rightmost digit. The positions are 2, 1, and 0. The digits are 1, 2, and 3. The corresponding weights are 64, 8, and 1. Calculate the sum by multiplying each digit by its weight and adding the results. This is 1 times 64 plus 2 times 8 plus 3 times 1, which equals 64 plus 16 plus 3, resulting in 83. To convert a hexadecimal number to a decimal number, consider the hexadecimal number FF with base 16. Assign position weights which are powers of 16 starting from the rightmost digit. The positions are 1 and 0. The digits are F and F. The corresponding values are 15 and 15. The corresponding weights are 16 and 1. Calculate the sum by multiplying each digit by its weight and adding the results. This is 15 times 16 plus 15 times 1, which equals 240 plus 15, resulting in 255. Here's a quick reference table to summarize conversions between decimal, binary, octal, and hexadecimal number systems. The table provides equivalent values for the numbers 0, 10, 15, 16, and 255 across the 4 number systems. For example, decimal 10 is equivalent to binary 1, 0, 1, 0, octal 12, and hexadecimal A. Similarly, decimal 15 is equivalent to binary 1, 1, 1, 1, octal 17, and hexadecimal F. Decimal 16 is equivalent to binary 1, 0, 0, 0, 0, octal 20, and hexadecimal 1, 0. Lastly, decimal 255 is equivalent to binary 1, 1, 1, 1, 1, 1, 1, 1, octal 377, and hexadecimal FF. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.